You see the little countdown there? Still counting. This isn't blinking. Sarah, is this thing supposed to be doing something? Oh, it is. You're live, sir. Okay, we're live? Okay, we're coming to you live from the Center for Excellence in STEM Education. It's great to welcome you here. We've got two specialist speakers today, two graduate students, Sarah Stegall and Gejun, who will be presenting to us. We're excited to have them here. We'll turn the time to Gejun, who is going to be talking about Bayesian statistics, and then we'll turn the time over to Sarah.
Thank you.
You can clip that mic right on your shirt. Gejun.
Okay. My name is Gejun. Oops. Give me this. Okay, thank you. My name is Gejun. I'm from the Maths department.
Today I'm going to talk about the Bayesian analysis in R and one-parameter model. And so if we want to talk about Bayesian analysis. So first we need to talk about the Bayesian rule, Bayes rule. Okay. And here's an interesting problem. Just as suppose your friend told you that he has great nice conversation with somebody on the train, and you need to guess the gender of the person he talked to, but you may guess that 50% that the person is a woman, right? But if he told you that the person has long hair, then you may guess the woman must be more likely, right? So, so if we want to find the exact probability of the what is the probability for that person is a woman, then we're gonna use the Bayes theorem, which is PAI given B is equal to the this is the formula, and the denominator is the total probability function, and this is the actually is prior probability, and this is the likelihood I will introduce later, right? So, but Bayesian analysis in R is different from the using the Bayes theorem. So Bayesian analysis is not just use the Bayes theorem, okay? So the next, just assume you are a skilled programmer, and you just compile the program. You maybe you be confident that the program will run correctly, but sometimes there's some bug in your program, right? So you want to find some data to test your program. First, you find 10 or 100 data sets. Then, yeah, it passed. You become confident, right? And then you find more difficult data to test your program. Maybe you find 1,000. Okay, it will pass again. And then you find more and more and much harder the data set to test the program. Yeah, it passed again. So you become more and more confident, right? The data give you the confidence. Right? So the Bayesian thinking is kind of like the testing the program. You find more data there, then you update your belief about your program, right? So this is the I think is the principle or the Bayesian thinking. in our daily life, right? So this is the Bayesian thinking. So for the Bayesian analysis, we use the belief, and so the F theta is the prior distribution which expresses our belief about the parameter before we see any data. But for Fx given theta is the statistical model which reflects our belief about x given theta. Sometimes we call this the likelihood. And the last one is the posterior distribution, and the x1 to xn is the data you got it. And then we after we see this data, we update our belief about the theta, the parameter here, right? So the posterior distribution can express our updated belief after the observing of the data, right? So we use the Bayesian theorem. Here you can see if it is a continuous distribution, we use the integral, and then this the same as the previously. So if we have independent identical distribution, the data there, usually we use ID observations xa1 to xn, then we get the likelihood, because this is sometimes we call it likelihood, right? So we use the multiplication of or the theta given xi. We use the ln theta. Summarizing to that one, because this one after the integral it must be a number, right? So it doesn't depend on this theta, so we can just use a proportion to the numerator here, right? So this is the basic ideas about the Bayesian analysis, and I'm going to introduce two models, one parametric models. The first one is binomial model, and the next one is the Poisson model. The binomial model is the prior distribution is a uniform distribution. This is the specific example, which the prior distribution is a beta distribution. It's a uniform, and a uniform distribution is a particular beta distribution, which is A is equal to 1 and B is equal to 1. And the likelihood function, we can see we use the previous here. We find the multiplication of all the fxi given theta. So we find the it's proportional to theta to the power of x and times 1 minus theta to the power of m minus x, and then we use the prior distribution times the likelihood function, then we get the posterior distribution, right? So the x given theta, after this theta, the distribution of the theta is to the beta x plus 1 and x minus x plus 1. And this is the beta distribution also. So if the prior distribution and the posterior distribution are the same distribution, so we can call this is the conjecture prior. Okay, and I will give you example. Then I will show this example in the R. So how to do that? This example is each male, female of age 65 or over in the 98 general social survey was asked to whether they were generally happy, and y is equal to 1 if the respondent I reported being generally happy, 0 otherwise. Okay, this is the binomial distribution. They only have two possible outcomes, and the data is the 129 individuals surveyed and 118 reported generally happy, and 11 did not report generally happy. So we can use we can see the model looks like this. This is beta A is equal to 1 and B is equal to 1, and this is the uniform distribution. Likelihood, we plug in the data because the success we're interested in is 118 and 1 minus theta, the which is not happy, is 11 people. And so the posterior distribution, we can see we use the probability times likelihood, and we get the beta distribution, which is 119, and the next, the other one is, oh, yes, 12. Okay. So we get use the R. See, the graph looks like this. The dashed line is the prior distribution, because this is a prior probability, because this is uniform, so it looks like X line here. And the posterior, which as we can see, is this, is beta 118 and 12. 119 is 12, I'm sorry. I'm going to show this in the R. If the prior probability is not a uniform distribution, it is a beta distribution, we can get this actually the similar results from the Bayesian analysis. So the prior is a beta distribution. This is the beta distribution, and if this is the likelihood, and this is the posterior distribution, you can see that is the posterior distribution is actually in the middle of the prior distribution and likelihood distribution. Sometimes we call this like I forgot this word, compromise between the prior and the likelihood. Okay. And the next model is Poisson model, and we also have the prior distribution, but this time the prior distribution is a gamma distribution. Gamma distribution, we can write it in this way. This is gamma function, and the theta to the power of n minus 1 and to e to the power of negative b times theta. And the likelihood function is we find the multiplication of the single Poisson distribution. So we get, because this part doesn't depend on the lambda here, so it only depends on the data here. So we just write the function c of x1 to xn, and it times the other part here, right? So then the posterior distribution is still gamma distribution, because they have the same structure to the other part. So we can write this posterior distribution as the theta to the power of a plus sigma xi minus 1 to then times e to the negative b plus n then times theta. So this is the posterior distribution of the gamma distribution of this, which is a Poisson model. And this is example for the Poisson model, and we have 155 women, and their age over 40. We're going to compare the birth rate between those who have a college degree and those who don't have a college degree. So for those who have a degree, we use y11 to the yn1 then 1. Okay, that means we have n1 women, they have the college degree. And for those without the degree, we use y11 to the yn2 then 1. That means there are n2 women, they don't have the degree. So they all follow the Poisson distribution, and the first one, the parameter is theta 1, and the second one is parameter is theta 2. And then so we can change the data to this form. So those who don't have the bachelor degree, n is equal to 1, and totally they have 111, and oh, I'm sorry. Totally they have the to 11% and N1 is equal to 1. They say that totally they have 17 and then 111 people have they have the less bachelor degree, and the second group they totally 66 people and 44 people have the bachelor degree or higher. So we'll compare these two groups, then we plug in all the numbers to the model. Then we just assume that theta 1 and theta 2 they have the same gamma distribution. The parameters A is equal to 2 and B is equal to 1, right? And then we got the posterior distribution as theta 1 is given the data, we see the gamma distribution is 2, 19, and B is equal to 112. And theta 2, then given the data here, we got the gamma distribution with parameters A is equal to 68 and B is equal to 45, right? So this is the graph of the gamma distribution in R. So this is the distribution of theta 1, and this is the distribution of theta 2, and this is prior distribution. So from this, we can see the prior distribution of theta 1 and theta 2 are the same, but after we saw the data, we update our belief that theta 1 follows this one and theta 2 follows this one. So the data will help us to update our belief about the parameter, right? So I'm going to show you the program in R. Okay. So let's see. I used R Markdown to do this this file. So we see here. So the first example we see this is the normal distribution. So we just set the two parameters A is equal to 1 and B is equal to 1. And then this is the what's this? So we're gonna see the people who say they reported they're happy, and and this is the not happy. The how many people they didn't report they're happy. So we use the H is equal to, because the number for here we can see 18 reported general happy and 11 didn't report general happy, so H is equal to 19 and not happy is equal to 18, right? So we're going to use the curve function, and this is the beta function. If the beta function, you can see if there is a D here, that means the beta distribution. And if it's Q here, that means quantile beta distribution. And if they use R here, that means you're going to generate the random beta distribution. That you're going to generate some like the sample data there, right? So the curve you see here. So this is the curve for the posterior distribution here, and then because we use A plus H and B plus NH, so you can see this is a posterior distribution, and then this is the prior distribution, which is the uniform distribution. So this is only a line here, and with the this here is equal to 1. So we add some legend to this graph. So that means the dashed line is the uniform distribution, and this is the posterior distribution, the graph of the posterior distribution. right? So this is the posterior distribution with the uniform prior, and then we're gonna see which is a better prior. So this time we'll set A is equal to some other number, which is not equal to 1. A is equal to 3.26, B is equal to 7.90. We're gonna see how does this graph look like. Let's see here, if right? So this is the posterior distribution. See, we use A plus S and B plus H here. And then because the beta distribution we for the first one, which is only the uniform distribution, so we don't need to just add 1 here. But for this one, this is beta, so we used S plus 1 because when we use the formula, we can see that one is theta plus 1. So we need to add 1 here. This one, and the next is this is prior distribution. Okay, we see the legend. So this is prior, and this is likelihood, and this is the posterior distribution. Okay, the same as that one. The last one is the Poisson distribution, which is A is equal to 2. We assume that the prior distribution with parameters A is equal to 2, B is equal to 1. So we said A is equal to 2, B is equal to 1. And then this is the first group. They have totally they have 17 people, and 11 they have the with the degree. And for here, this is the second group, 66 people, and 44 they have the high degree, right? Yeah, bachelor's degree. So the curve we see, yeah. Oops. Is that where? Oh. Oops. Let's see. Is equal to. Oh. Did I wrong here? No. This part. Oops. Doesn't work. Oops. All right. So I want to use that one. Okay, so this is the gamma distribution. We use the D means that the gamma distribution. So this is the posterior distribution, and then for here this is prior. See here. All right. So this is prior distribution, and then this is the second group, and we can see the posterior distribution. And for the legend one, for the legend here, I spend a lot of time because there are some math expressions here. So this is the this is for theta 1. We're gonna see the posterior. Oops, doesn't work. So first, previously we see the theta 1. We have the prior distribution with A is equal to 2, B is equal to 1. But after we've seen the data, we see it becomes 1.95 and 5357, right? So, and this is the mean of the, should be here. So this is mean of the first group. And this is the quantile. It's quantile gamma distribution. We use Q gamma. Then this is the interval, confidence interval, which from 0.025 to 0.975, right? This is So it's between 1.70 and to 2.2 here. So this is 95 confidence interval. And for theta 2, we're going to do the same thing here. So for the posterior mean of the theta 2, we got 1.5. And then the mode is 1.48, and then the quantile 95 confidence interval, we got 1.17 to the 1.89. Okay. And then if we use the prediction for these two groups, we use some data to test it. This is theta 1 predict. We use you can see the dn binomial. So this is the binomial distribution with how to say this one? Is the nominal binomial? Negative binomial. It's the negative binomial distribution. So because yeah, density of the negative binomial. I forgot to introduce the here because so after this no, it's here. After this is the negative binomial distribution. Oops, it doesn't work. Okay. So negative binomial distribution. This is y and this is size. Size equal to, we plug in all the numbers right here. So y, we just said 0 to 10. And then we see from this is the, oops, I didn't run this, sorry. And all right. So this is the prediction for theta 2. And then we're going to plot this 2 to see. All right, let me just run this together. Oh. So you can see this is the prediction for the y n plus 1, because we know the y1 to the yn, but we need to predict the yn plus 1. So this is the graph we're going to take a look. And it's not very clear for the color here. This is one, it's black one, which is less than the bachelor degree. And this is the bachelor degree. So you can see for here, they have the bachelor degree, the person have the bachelor degree have the larger probability than the less than those who didn't have the bachelor degree. Right? So this is a prediction for the probability of the y plus 1. So I think this is only part of the Bayesian analysis, and I don't know whether I explain them clearly. So if you have any questions or problems, just let me know. Okay, so that's it. Thank you.
Okay. All right. We should at this point be able to hear anybody in the room. We don't know for sure. We're still experimenting. Are there any questions that you have? All right. Thank you very much. We will now hear from Sarah Stegall. Changing the microphone back.
is on the website.
Oh, lovely. So like this. Thanks. Forward and back. Hi everyone, my name is Sarah Stegall. Unfortunately, I don't know all of that advanced math that just took place, but it was really, really cool and I really liked the graphics. What I'm going to be doing is mainly talking about what you can do with your data, 2 different data sets to put it together. And this comes from a problem that it happened to me in the real world. I was off doing my research and I was given 2 data sets on the same topic and the same participants. And I wanted to look at those 2 data sets together. So what I'm going to be talking about is how do you do that in R? And I'm going to be looking at the merge function. Okay, so give you a basic description, as I said. What you're doing with this merge function is that you are able to combine 2 different data sets that have 1 common variable. So that's a key part of it. It has to have at least 1 common variable. These are some of the examples of how you can type it in, but I'm going to skip to either arguments because I think this is more meaningful for us. So you know what the function is. It's just merge, and you'll continue to put in whatever is next. Right after merge, you need to put in whatever data sets you're going to be using. So data set 1, data set 2. Following that, you can put in your arguments, and the ones that I'm going to be really talking about is the all argument, which means do it for all of the data. Okay, so that's the only one that really pertained to me, so I really went in depth in kind of looking at that. But there are several other ways that you can look at this. You can look at it just merging things on your first data set by using an X, by using .x, or you can use .y for doing things with your second database. But for me, in the circumstance that I'm going to explain to you, I'm going to be doing it across all of my variables, across everything, because I want everything from the first data set on the participants and everything from the second data set to merge into 1 comprehensive file on all of those participants. Okay? So I used this example that was given by Oscar Torres Reina. He has a really good group of slides together that actually gives you a lot of visuals. So rather than show that all to you again, I'm going to give you this example, and the link, if you click it, will show you all of the examples that he gives you. And he goes step by step, looking at this is the data set 1, this is the data set 2, and this is what you get as your final picture. It's really, really useful for visual people like me. So if you're kind of like that as well, this is a really good source for you. So as I had just explained to you, as far as putting in your information, data set 1 and data set 2, if you put everything in there, just putting in your data sets and you don't put any arguments, what you're going to be getting as your result is just the common cases within those 2 data sets. So an example of this would be is if I had a data set with 2 participants and they had a common variable like gender, it would just merge what was common. It wouldn't include all of the other cool stuff that I put in there. It would just be gender. So we want to include this all command, which is what I'm going to be using in my practical example, including all. And we want it to be true. And by doing this, it's going to merge all the cases from both of those data sets, which is really, really what I wanted to do, right? Additionally, I did mention to you that you can do things just looking at one particular data set, like your first data set versus your second data set. And if you wanted to do something along that lines, because maybe what you're trying to do isn't what I'm trying to do, you can do that by including the .y or .x in your arguments. So there is some things that you can do to make it your own. And of course, if you want to see your data set after you've done it, because I'm a visual. I can't just trust to make sure that it's there. I have to see that it's there, right? You can go to view your data or just type in your data set's name, and you should be able to just double check, which is always good. Double check, make sure everything is there. Go ahead.
Sure.
Yes?
So the
Those are the data set's names. Oh. Okay, so his question was about what V1 and V2 is, and maybe I'm just going way too fast. Let me break it down a little bit further back. Whenever you're merging 2 data sets, there's this by command. I don't think I mentioned this. That's whatever variable you're going to be merging into. So, for example, if it was gender, you would put in gender as the name of your variable. So you put like the combination, you'd use a little c, parentheses, and you put it in your quotation marks, and put whatever it is that you named it, and then afterwards a comma, and then whatever else you wanted to merge. Because you can actually merge multiple variables as long as it's listed with that by command. Yeah. Yes. So an example of two data sets that you would want to merge, I'll use my practical example because this is right along the lines of that. So the data set that I'm using, it was multiple samplings of the same group of participants. But whenever I got that information, it actually came out in separate databases instead of being in one data set. So I really want to compare, you know, between that first testing session, the second testing session, and third testing session. But I can't do that with the way that's currently set up. So I have a bunch of variables in there, like, for example, like score 1 for the first testing session, and that second document I have score 2 for the second testing session, and I have a common denominator in between the two of them, a common variable, which is like their ID number. So I go with that ID number and I group them, all of those data sets together using the merge command, putting in that common variable in that by argument, and then it merges them all together. So I would have ID number, score 1, score 2, and score 3, which is ideal rather than looking at a whole bunch of different data sets. Okay, does that answer your question? Well, we'll kind of get into that a little bit. The example that I'm going to give you using R, I'm sorry, your question was like, talking about like unique identifiers and unique variables. R is pretty smart, as you probably know, and if you have something that is identical, and I did this in my example on purpose, I called, in dataset 1 I have a variable named variable. I'm really clever. In dataset 2 I have a variable named variable, and whenever you merge them together, what it does is it puts a dot x or dot y behind it. So your dataset 1 is going to be x. So for that dataset, the variable that was in there is now going to be variable.x. And the second dataset that I have, the variable is also named variable. It's now going to be variable.y. Okay. Any other questions? Okay. I'm speeding along, so I'm sorry. Well, you're asking about which one, and x and y, which is what, or where is what. So I'm going to go over that by just explaining this in brief. So merge, you're following merge by whatever the names of your data set is. So if you have some extravagant name of your data set, maybe it's testing session 1, that's going to go there. Then maybe testing session 2, that would go there. And then 2 data frames. And that's really all that this function can do, is just 2. And we'll get into, like, whenever we go over the summary videos, of ways that you can get around that annoying hassle. If you have 14 databases, you want to have one data set, you'll have to import all 14 of those and then run this function 13 times, which is annoying, right? We'll go over in a video. There's a user who has come up with some function in order to get all of that to work in one command, one little line. But you would be correct in saying that. If you were to have multiple data sets, let's say you have 5 or something, if you have 5 different data sets, you have to run this function 4 times. So you would first combine 1 and 2, then what you created with the 3rd one, and then what you created with the 4th one, and then what you created with the 5th one. So see, I was not aware that SPSS kind of works the same way as this, because I've never tried to merge different data sets in SPSS. I'm trying to move myself to R by forcing myself to do my research in R. So it's a learning curve. But anyways, does that answer the questions that y'all had about the function, since I kind of went over it real quick? Okay, I'll continue on and we'll go past the arguments. These are just the different all arguments. We talked about by. I don't do any suffixes or anything like that. And then this is the different examples I gave you as far as what you were going to be using and what you would get as a result depending on that all argument if you'd included it a particular way. Is there any questions on that? Okay.
So you see V1 and V2 are data.
These are going to be the variables. The V1 and V2 is whatever variable you have that's common in between those two databases. Right. Yeah, so an example of the unique variables that you could have would be like your participant ID number, or maybe you ask them what teacher you're taking this test for, and you ask them that twice. You could use that also in there as a duplicate variable that's in both of those data sets that's spelled the exact same way.
Also, sorry, this question might be no. So now, if you have V1 and V2,
Mm-hmm. Right.
So, but for V1, in V1, you have like multiple years, like 91, 92, 93 to 99. Okay. So in V2, it doesn't start from 91, it starts from 95. So is R going to pick 95 in V2 and align it 95 in V1?
I think that you might be referencing a different command. Are you talking about taking, I guess, information from a different set of rows and then moving information from another variable beneath those rows?
No, I think he's worried about matching them. And what it will do, it will ignore that data from 91 because it wasn't in that next one. You'll lose that. And then you'll match the 95 in the one with the 95 in the next one.
So, but what if you want to keep the 91 to 94?
I don't know. I'll have to ask an expert about that. But
Expert does not have an answer to that question.
In SPSS, there's a distinction between adding cases versus adding variables. I think this kind of gets at what we're talking about. So does this function that you're going over kind of have the option to either add cases with the same variables or add new variables with the same to your same case?
Both.
That's how
So-
merge your traces or merge your variables.
Right,
There are two
right,
functions
yeah,
in SPS.
right.
And that's it.
So
This does have the opportunity to do both. It can add new participants and it can also add new variables. So in the example that I'm giving you, it was very complex because we had some people that wanted to go to test session 1 and then also go to test session 2. And then some people, for some reason, only went to 1 and not 2. And then some people just went to 2 and not 1. So it actually, in running this one where it had all true, it'll add whatever participants were there for all of the data sets. And if they're missing on one, then it just has an A for all of that data set that they were missing.
thank you. I said something wrong about that, didn't I? Thanks for correcting.
Okay. Was there any other questions before we keep going? Okay. So I'll get to my example.
Hopefully this will work, Mark, because sometimes I get a little iffy using other computers in R with your workspace. So I'll just exit out of this. And I'll go ahead and open it up just for reference so we have it on the side. Exit. I think I'm making it mad. And we just want a small show. Okay, so I'm going to add in my data sets. I've abridged them and basically reduced them down to nothing, so I'm sorry that this isn't going to be very interesting. But, where's the import here? Oh, there we go. Thank you. And that's what I want. So my variables, I'm going to have one that's just an X, and that's going to be the ID number that I assigned them. This is going to be their gender, and then I have a random timestamp in here, and then that variable that I told you that I cleverly named variable, and it's also in this database. I'm going to import that, and this is going to be data set 1. And let's do our second database. So very similar. This one has also that ID number. This is going to be the common denominator beneath the two data sets. Then I have a second variable, Likert scale, another timestamp, and then the variable named variable. So let's import them both. All right, so we got both of them in here. So we've just completed importing our data sets, which was the first thing that you should do. You have to import whatever two data sets that you're going to be merging into R. Yes? I just wrote it out, so sorry. Yeah, so we have someone that mentioned that you should use capital V, so that is a correction. Oh. It's a capital V down here, but I've never really... Could not find function, so you are correct. Always use capital V. All right, so we've imported the two of them, and the next part is just to merge them. So let's go back to where we were, and we can reference. What we're going to be using to merge them is just that merge function. I'm going to be naming the two databases that I have, and then my variable name is X, because I actually didn't name it. So R named it for me, and it named it X. So that is our ID number variable. So I'm going to reference that as the common one in between them, and then I want to import everything. I don't want it to just focus on that first data set or the second data set. Every variable, every participant, I want it in there because I want to see everything. So I'm just going to put in this, my merge. I don't think I can copy paste from here. No. So I don't know why I just didn't put this in my file. And I messed it up somehow. Let's see. It's just so huge. Does anyone see my error? Where? It's capital X. And this isn't it, but you think where? Here? Okay. Oh, thanks. Okay, so that should be right. Well, let's give it a go. So I think that we've just created a data set, but I think I got rid of the other page here. Let's just view. Capital V, right? So this is what we created. So you should see this is our ID numbers. So this is all unique identifiers. This is our first variable in that first data set, which was gender. Second variable that we had in the first one was just our timestamp. And then you can look at the variable that I named it the same as the other data set. It did rename it to specify which data set it was taken from. So the first data set is going to be X. So after variable, it has .x. And then it has our other variables from the second data set following that. So the Likert scale, the timestamp, and then the variable again where it was named the same. This time it renamed it .y. So it's from the second data set. Okay, if you were to have multiple data sets, for instance, if you had 4 or 5 data sets, you would have to do this each time for each one of those data sets. So in the document that I have available for you, I have some supplementary explanations provided by Dr. Watkins, so thank you, Dr. Watkins, for providing these for us. They further go over how to merge data in case I blurred it or messed it up. You never know. I could have misspoken somewhere, but these people go over it pretty well, and they actually have people that peer review them pretty extremely on YouTube, so you can click on them and watch them if you'd like to. One that I would like to point out to you because I thought it was really interesting is ways that you can merge multiple data sets using one code and a short, line. So it's going to be in this one here where it says user-created multi-merge. And you can see an example of how he uses it, and he also explains it on his website. It's a little bit further down. But he explains how you use it and also gives you some tips on using it. But he does mention in his commentary that a word of warning for using other users' functions, and he always suggests that it's fun to create your own function. So if you're very eager and very R-driven, perhaps you can create your own as well. Okay. Well, that concludes my presentation. Is there any other questions as far as like what I did or what I confused you on?
Cases.
Yes. Yeah, so the question was, did I actually add cases? And as I mentioned earlier, I had some people that did not complete one of the sessions, and they are actually at the bottom. So you'll see that they have this first 3 completed, which was that first session, the first variables in there, and this next 3 variables, those were from that second data set. They just have NA, or it's nothing.
That data wasn't in the second data set.
Correct. So it was in the first one. They had something there, but they never did the second session. So it still imports their unique identifier and everything that they had in dataset 1. But when it goes to dataset 2, it's just blank. It doesn't list anything for them because there was nothing there for them.
So can't we drop that when you are writing code? Can't you tell R which variables to keep?
If you wanted to get really specific, and let's say you had everything set up in your first data set, you only wanted to look at data set 1, that's whenever you could use that .x, and that would look at the first variable set. If you want to look at the second data set, you could put .y, and that would focus on that second data set. But it is limited to 2 data sets, unfortunately, which works for me because I only have a few. But if you got a ton, I'm sorry. And it might be a good investment of your time to look at that multi-merge.
Did both data sets have gender as a variable?
Yes. So this one down here, I think all of them actually have the variable name itself. But as far as like in the data sets, my original data sets, the 2, the first one was more demographic information, so it included gender. My second one did not include gender because it was more just the scales itself. So it is listed in the data set, but if there's information there or not, it's really up to if they completed that first one or the second one. If I would have...
Both data sets had gender as a variable. Was this still a merge?
You could do it really easily. Remember how I listed you could put in like 2 different variables, add a variable 1 and variable 2? I only listed 1 variable, which was the ID number whenever I did my merge. If you had 2 variables, for example, if you had ID number and gender, you would put, for example, ID number as your first variable, and then you could put gender as your second variable, and it would merge those 2 together if it was in both data sets. So the key part is it has to be in both data sets, it has to be spelled the same. It would probably be a good idea if also the content was the same,
Sorry,
but it is possible to do those things.
Sorry, that was my first question initially. That if you are merging 2 data frames or data sets and you have 2 unique identifiers in each of the variables, right?
Mm-hmm.
So why do you have to use the 2? You can just use 1 because 1 is sufficient to match the 2 data frames. So here you are using the 2, which that's why I don't really know what value. Why do we have to use the V2? Because I think my understanding is V1 and V2, those both variables are in the two data frames, right?
Right, correct.
So, and they are unique, right? So why do you have to use it too? Why not just V1?
It's really your personal preference as far as like how many you wanted to use, because you can actually use as many as you wanted. If you want to use one, then use one. But if you had in your data set, let's say you asked them the same series of questions, like 3 questions, every single survey, the same thing. And maybe it was just information, so you would make sure that you were matching them up correctly.
Mm-hmm.
You would include those 3 variables in there.
Because if you use just one, it's going to include them anyways.
It will. It'll just put after it .x, .y. You have a question?
So the variables that you put in there will, in your newly merged data set, you will only have one variable from each data set.
That is my understanding.
So it probably doesn't make sense to just keep that as your ID number, just in case somebody did something like say they were male at time 1 and then say they were female at time 2, then
Yes.
you might want to focus more on the rest of their data.
So
Right, as a researcher, that's a good question to think about.
So
So
my
you're not
unders-
covering. Go ahead.
my understanding is that the reason it has V1 and V2 is because they might be the same thing, but maybe they're named differently. Like for example, an ID, maybe in one data set you might have it as uppercase I, D. In the other data set you might have it as lowercase I, lowercase d. Even though they're they're the same thing, but it's different names. So that's why you would specify V1, as belonging to my
But
data one.
that is not advised. You should make the variable
Name be consistent.
be consistent.
Yes.
So I'm going to refer
very
you
consistent.
to the document that I referenced earlier as far as like explaining it, because I'm very visual and this person had visual stuff, and I was like, I'm going to go with this. So this person has a lot of visuals explaining and actually showing you what happens, because I think seeing it is a big part of believing that it's happening. So it goes step by step and saying what code are you putting in using 2 variables, and it breaks it down using country and year. So these are 2 different variables, not spelled in any different way, 2 completely different variables.
Okay, so this is my question. Sorry about that. Oh, I can talk to you if we run out of time. Do we run out of time?
We,
Oh, I'm sorry, it's just so intriguing merging data, right?
It is, this is exciting. Let's close our video at this point, and then we'll have a quick business meeting, and then we'll do some further discussion until they kick us out.
Okay.
That sound okay? Yeah.
That's great. Thank you for the questions. It was very nice.